Hello everybody and welcome to our viewers worldwide that today gathered to listen to how Webcast 3D packaging is transforming the world of semiconductor packaging, powered by YOL Development, System Plus Consulting and Samsung Foundry. I'm Faisal El-Kamasi. I'm a Global Sales Support and Coordination Manager for YOL Development. Before we get started, here is how our webcast will occur. Our session today will last about 1 hour, during which Favier Shaw, Team Lead Analyst Packaging at YOL Development, will make his 15 minutes presentation on the market technology trends and supply chains of 3D packaging. Belinda Duby, Technology and Cost Analyst at System Plus Consulting, will also make a 15 minutes presentation on packaging technology analysis, where she highlights the hybrid bonding technology. We will continue with about 10 minutes presentation of Max Min, Director from Samsung Foundry, about Samsung's Foundry Cube technology for heterogeneous integration. Finally, we will finish with a Q&A session of about 5 minutes per speaker. Before we get started, I remind you that you are encouraged to submit questions to our analysts during all the live event using the Ask a Question window at the bottom of the screen. Questions will be answered right after the presentation. In case we don't have time to answer all of them, we will follow up with you by email. To conclude, this live event is recorded. You will receive tomorrow an email with the link to access the recorded session. So let's start the webcast. Favier, the floor is yours.
Hello everyone. Thank you, Faisal, for the very nice introduction. I'm Favier, the Team Lead Analyst of YOL Development. Today my topic will be covering really the market and of the 3D packaging, and also follow up by the supply chain, market forecast, portion of this market space, and ends off with a conclusion. The outline of this webcast is as shown here below, and I will go straight into this right now, into my next slide. I'm showing here is really a chart of the overall semiconductor industry trend, illustrating the number of leading-edge manufacturers from 2002 onwards. But before that, I would like to also briefly touch a little bit of the history, because you know that since 1965, Gordon Moore has actually made a prediction that the number of transistors per dense integrated circuit doubles every 2 years as the technology progresses. So this law, which is like a golden rule for the electronic industry, has been a standard that the manufacturers are trying to keep up. So for the past decades, Moore's law has guided this global semiconductor industry, improving both the performance and cost through this node scaling. But as you can see from this slide, after 2002, which is a 130 nanometer, industry has been consolidating pretty extensively. And there's limitation, because there's limitation in the scaling, which has disrupted a lot of the company's capability to compete in this business without heavy investment. So if you look at now, presently in 2021, it is currently now an oligopoly market with just a handful of key players, namely Samsung, Intel, and TSMC. So we also know that, the cost of building, say, a new facility of 5 nano production lines is expected to be close to about 5.5 billion, which is 5 times more of that of 20 nanometer fab back into years ago, right? So such a heavy investment, just steep cost, is actually the main barrier to entry, and it's also why the reason a lot of the players are falling out of this advanced scaling race, right? So now I'd like to further introduce you that point on how steep the investment cost can be, and also show you the packaging value that comes into play. So in this chart, you can see like the timeline since 1970 to we forecast to 2050. The data between the technology nodes on the right and also the 3D interconnect density of the system level on the left. So we can see that Moore's law remains like alive for over like 5 to 6 decades now, and has created this industry expectation for performance increase, but is no longer cost efficient when it comes to advanced nodes. And as shown in the previous slide, and the node scaling is actually slowing down. So traditionally, the IC industry, kind of rely on the traditional chip scaling to an innovative architecture to innovate, to advance the new devices. But in this chip scaling, the idea really is just to pack more transistor on the monolithic die, SoC, at each process node. But this traditional way of scaling has become really difficult and expensive, node after node. So while this scaling continues to be a very important work in progress in the background, the industry is now looking to utilize the advanced packaging technologies to have a multiple advanced and mature chips packed into a single package, such as like heterogeneous integration, 2.5D, 3D packaging, to extend the 3D interconnection density. And hence you can see the packaging value is actually the bracket area in yellow, where you can see with the 2.5D 3D scaling, you can actually bring up the overall 3D interconnection density to the next level. So, the advanced node scaling combined with this high-end performance packaging, it can actually really bring the overall system level 3D interconnectivity breakthrough into an inflection point where we believe this will be the key focus moving forward in years to come. And this is really the value of the advanced packaging where we're looking at 3D and 2.5D scaling. I'd like to further touch on the market drivers for 3D 2.5D packaging. This really includes the adoption of the cloud and edge computing. As you can see the timeline from the left to the right, we're actually having the I/O density on the Y scale, illustrating the different kind of technology bracket is allocated color in the legends on the right to further show how this evolution comes about. So yeah, one thing that we noted is the increased adoption of the cloud and edge computing in the devices, which increase such implementation on the end system units in this area like high performance computing, HPC, especially in the consumer devices, personal computing, and gaming. So there is strong R&D effort to drive the advanced packaging towards this technology like TSV, 3D stack memory, 2.5D interposers, ultra high density fan-out, embedded silicon bridge, 3D SoC, hybrid bonding, and each motivation is trying to bring the I/O density to the next level with more functional integration, in a way pushing the limits into the higher end of the space. So if you can see really what we expect moving forward is more complexity and synergy of this packaging technology. And yeah, so what we're seeing now is industry is really seeking different creative way to design and manufacture the latest SoC with a system package format or chiplet-based approaches in this high-end packaging platform. And it will definitely be a mixture with what we foresee and what we believe is that there will be a mixture of latest and immature devices. And as such, 3D packaging and 2.5D packaging is really accelerating the technical breakthrough for 3D interconnect density. Now moving on to the supply chain. The supply chain is very interesting for the 3D packaging, high-end packaging, because it involves a mixture of leaders of different business models. So if you look from the left to the right, you can see that left side is the front-end players, And on the right side, you have the back-end players. Front-end players, typically we call them the bigger players, of course. They have more financial muscles to flex, being the IDM and the foundry on the right side. Back-end, you can see we have OSAT and the substrate suppliers. But here comes the middle end zone where it's typically a wafer level packaging where all the different players can be involved. Because with these packages done at wafer level, the players are dedicated, with those dedicated with front-end wafer equipment are now able to join the packaging supply chain. And with the same objective to enlarge their scope of action, back-end players who are usually accustomed to underfill IC substrate dicing molding are now trying to go further up the supply chain in their processing steps, since now package can start earlier in the manufacturing chain at wafer level. So this middle end zone between front end and back end where bumping and packaging can be executed on wafer level, just for example, TSV, RDL, thinning, hybrid bonding, fan-out, fan-in, all can be reached by OSAT, wafer level packaging houses, and IDMs. So now for this high-end packaging, it's now inseparable from front-end technology. So building the next generation of business outside the traditional scope is now necessary. Okay, to the next slide. This slide shows the map of players based on technology, but this is more of like showing the packaging landscape by I/O pitch and the I/O density. So you can see like from the left to the right, we have ultra high density fan out, break up with the the manufacturers involved, 2.5D interposers, 3D stacked memory, being the TSV and micro bumps, embedded silicon bridge, and eventually the hybrid bonding. So we believe like for this middle end zone, there is definitely a lot of different synergy and creative integration and technology that can come about. So I think the point here is really to look at how this different next generation of stacking, be it 2.5D or 3D, how it involves the different capability between front end and back end. So, big players like Samsung, Intel, TSMC has actually successfully tapped into this high-end performance packaging market, and they are actually achieving a lot of the faster time to market than OSAT at really an unprecedented level. All right. So now going on to the next slide where we're looking at the IP landscape done for hybrid bonding 3D SoC. So, as hybrid bonding and 3D SoC are projected to be the future of 3D packaging, it kind of like not a big surprise that more and more companies are trying to secure their patent in this space. So the interest in IP landscape for the hybrid bonding and 3D SoC has been rising. And as of now, you can see like we have players of TSMC, followed by YMTC, Xperi, Samsung, SMC, Sony, Samsung, Leti, etc. So all these players are trying to lead the way for the hybrid bonding 3D SoC, and we see like in a nutshell, these companies are slowly gathering the secret weapon to slowly exclude the other manufacturers from hybrid bonding 3D SoC domain, because eventually this will lead to royalties generation through licensing, or it can be a block for a different kind of competitors to join this game at the early stage. Now moving on to the market forecast of 3D packaging, but I'd like to bring your attention on how we split the market, because not all 3D packaging is high-end. We have, if you look at this, we have actually the high-end segment and the mid and low-end segment, where high-end segment we are typically looking into HPC and networking and gaming, while mid and low-end segment is sensing and lighting. So for high-end segment, we define the market where application is less sensitive to the cost and require a smaller footprint in addition to high performance and reliability. So our market forecast in the following slide will be mainly based on the high-end performance only. All right, so moving on to this slide where we show the total market forecast revenue for high-end packaging. You can see that the high-end packaging market is valued at 0.8 billion in 2019 as projected to reach 4.7 by 2025, with a CAGR growth of 32% from 2019 to 2025. Such strong growth is pretty much attributed to the fact that this high-end packaging has become an essential part of the semiconductor packaging supply chain, allowing the integration of diverse dies across multiple process nodes and really achieving similar performance as a monolithic SoC, expanding the Moore's law at system level at a 3D interconnect system level. So, in this field of the high-end packaging, this has really led to the emergence of Samsung, Intel, TSMC to join the game to start to invest and start to grow this market space. So moving on to the next slide, you can see this is the further breakdown of the different end markets. So the biggest market for the 3D packaging comes from the telecom and infrastructure, right, accounting for more than 50% of the market share from 2019 to 2025. Among these prominent, digital age demands, high-end packaging drivers are coming from really the increased implementation and interest in the cloud computing, networking, HPC, especially in the consumer, personal computing, and gaming portion of the market. So, in addition, the growth in the mobile and consumer digitalization and increased adoption of Internet of Things, mobile connections, smart objects are expected to present major opportunities for the expansion of this high-end 3D packaging at device level. So they all need a fast, big memory that interacts quickly with the processing units. Just for example, like in the advanced gaming computer, TSV are deployed in the 3D stacking of the DRAM and HBM. So with the GPU, they equip the GPU, this high-speed memory, and the high-performance gaming can be achieved. And also, we know that we have Apple releasing the upgraded iMac Pro that integrates the AMD Radeon GPU, and also YMTC have the hybrid bonding in their hard disk, and Intel with the Foveros in the laptops. So these are all the different examples that you can see how this further evolves. So really now we are expecting to see a larger portion of penetration of high-end packaging into also the automotive and artificial intelligence and robotics in vehicles. Conclusion, we know that the 3D 2.5D packaging has really become the primary driver pillar of the semiconductor industry right now, because it's been looked upon as a way to extend the Moore's law, a slowing Moore's law. And in this acceleration towards a new level is where the value comes about for the 3D 2.5D packaging. And we know that at this moment in time, more digitalization requires really a more intelligent, multifaceted devices, which enhance and further solidify the trend towards this area. So leading companies like the listed company here are really starting to place a lot of priority, as you can see from the IP filing of their hybrid bonding 3D SoC, which is viewed at the next generation packaging. And the growth is expected to be really strong, as you can see, going from a rather relatively smaller market as compared to other packaging, 0.8 billion to 4.7 billion, with 33% CAGR growth from 2019 to 2025. So yes, this marks the end of my presentation. Thank you, everyone.
Thank you. Thank you very much. Very interesting presentation. Now it's time you with Belinda. So please, Belinda.
Thank you so much, Faika Packaging. I am mostly going to concentrate and highlight the hybrid bonding technology used in packaging. So how is my I'm going to first start with the introduction, where I look at the packaging trends, and we'll also look at the heterogeneous packaging, the 2D and the 3D type of packaging. We will also look at the TSV technology. Mostly I will concentrate on the hybrid bonding technology, where we look at the process. This is the process technology, and we're also going to look at the Favorous technology, direct hybrid bonding for CMOS image sensors, and also for memories. And we are going to look at the advantage and the limitations of this type of technology. And after all, I will give a conclusion. Different technologies that we have. The packaging trends are mostly influenced by the packaging needs. Higher package integration is needed for enhanced functionality of devices and higher power density. Increased speed, reduction of switching losses, and better heat dissipation are actually influencing more and more the package design. As we can see, we're getting to have more complex package designs that we have, like the 3D and 2D, 2.5D type of package. Right now, let's look at the heterogeneous package, which includes the 2.5D and the 3D package. The component includes an interposer die. This is reverse costing that we did on this type of component, where we actually opened the component, and we see that the component includes an interposer die that is integrated to achieve the communication between the chips in the package and the board. And the HBM memory that is actually sent here, we had 5 HBM memories that were included in the package. So the NVIDIA package is almost 40 gigabits of this type of memory. The HBM memory are actually stacked one on top of the other. These are the memories, the DRAM memory. This type of heterogeneous package is used in the high performance computing, where the package integrates a GPU die and a memory component. As we can see here in the bottom screen, we have the cross-section of this type of component, where we see the HBM on both sides and the GPU die that are all sitting on the interposer die. So let's look at the connection between the dies. The vertical interconnects using silicon via, as they enable high density signal routing and fast speed of the memories. The silicon wafer is actually etched, and the trench is then filled with the copper material, and then they are connected using bands. So here we have 2 different generations of the HBM DRAM die that we have here, where they are connected. We see that the pitch is becoming a concern. Fine pitch is required. As the packaging technology advances, the TSV pitch reduces. As you stack more and more dies, you need faster speed, and this speed is becoming more important. So more TSVs are actually used that result in smaller pitch on the component, which in turn affects the TSV aspect ratio. TSV thickness is reduced, and the etching could become a concern. So here I am going to highlight more of the hybrid bonding. We are going to see the different technology and the different players who have adopted the hybrid bonding, and see their advantages in using this type of technology. So hybrid bonding has actually been used for some time now. We have old and new applications and also different benefits. And we're also going to look at the sneak peek of the cost of this technology. Hybrid bonding is used also as a scaling method. 2 complex chips are bonded together. There are different types of direct bonding that we have in the industry. we can look at there is the fusion bonding, the anodic bonding, the copper-to-copper hybrid bonding that is done at room temperature. This is the one that we're focusing on. So in the next pages, we'll look at Sony's CMOS image sensor and YMTC that also joins the hybrid bonding technique to make their NAND memory. So there are two types of bonding techniques that we're seeing in the industry. There is the wafer-to-wafer type of bonding, and also there is the die-to-wafer type of bonding. You can also find a die-to-die, but I am not going to focus on this or talk about this part. So here, when you are looking at the wafer-to-wafer bond, the dies actually have the same die area because you are putting two wafers on top, one wafer on top of another wafer. However, the yields are very low because you are bonding untested dies. Both the good and the bad dies are bonded together. So we're looking at die to wafer. So this part is really interesting because you only have the good dies that are going to be bonded together. Therefore, you are going to have yield advantages when you come to die to wafer. Die to wafer also means that the die sizes could actually be different as we are going to actually dice out the dies of one wafer, pick and place them on another wafer. So die handling is also becomes an issue in this, and also particle management could be a challenge in die to wafer type of hybrid bonding. Foveros technology is actually used by Intel to bond two dies face to face. One example that I'm going to give here, and that you can see actually on the cross sections that we did of an Intel component, we have the chip on wafer on substrate type of bonding. It is used by Intel components. The processor die is actually flip chipped on the interposer die. The copper pillars and solder connect to each other to form a strong connection. High interconnect density is then achieved by this type of technology. And wire parasitics is actually eliminated when you use the Foveros type of connection, which is very important in the high performance application. So here we have the hybrid bonding that is actually used by Sony on their CMOS image sensors. So here we have the pixel array circuit and the CMOS circuit. This is the logic circuit that is actually bonded together. So here we have the copper-to-copper hybrid bonding from the two wafers that actually come together to form a single component. So what we did here, as you can see on the far left of the screen, you can see here how we separated the two dies that were found in this component. So we're actually able to actually take out the pixel array circuit on its own and actually the logic circuit that was actually bonded together. So when we look at this type of technology, we tried to estimate the cost of this component. So we actually found almost $4,000 US dollars that was estimated for the CMOS image sensors wafer cost. And how did the hybrid bonding take part in this cost? We estimated less than 15% of the total component cost actually was attributed to the hybrid bonding technology cost. So here, let's move on to the hybrid bonding that is actually being used by YMTC. So this is the application in memory that was actually used by YMTC. So YMTC, what did they do? They actually made the logic wafer on its own and actually made the NAND array wafer on its own and joined together in this hybrid bonding technology using the hybrid bonding technology. And this is actually different from the other manufacturers that are actually using the NAND array wafer. They are building the NAND array cells and the CMOS and the CMOS transistors on the same wafer. So this actually means that more space is actually being used also by the CMOS transistors on this wafer. So how did they have a win using this type of bonding in this application? For the NAND memory, as we can see, the different manufacturers here, we estimated their density for the 64-layer memories. They all did not achieve 4.5 gigabits per millimeter squared of density, except for YMTC that used this type of technology. So we can see also that this type of technology being used for memory applications is advantageous for growing the memory density in NAND memories. So here also we look at the direct bonding. This is a cross-section of the YMTC type of memory. So here the metal layers they form, they are used as a pad to join each other. So here they are joined together at room temperature. And actually we have an interconnect that takes part in the last metal layer of the CMOS wafer and the last metal layer of the NAND wafer. And also here we did make a cost estimation of this type of hybrid bonding that's in memory. So here we take into account the cost of the CMOS wafer, the cost of the NAND array wafer, and the cost of joining them together. And here we see that almost 14% of this cost, this total cost, was attributed to the hybrid bonding, where they are bonding the two wafers together. So this cost was not a large sum compared to the overall cost of the memory. Let's look at the win points of the hybrid bonding. So this type of bonding results in devices with better properties like improved bandwidth that we have. We have improved bandwidth, and it's actually being done at low temperature, which means there is no risk of degrading any of the cells or the transistors. And also it has very good cost advantages, as we saw when we estimated the hybrid bonding cost in memories and also in CMOS image sensors. And the yield is actually a concern. Unlike traditional packaging methods, which have micrometer size defects, hybrid bonding is actually very sensitive to nanometer defects at nanometer defects. And we also have reduced yield because this technology is not really mature. And alignment accuracy is very important when we come to hybrid bonding, where the pads need to be exactly positioned together to improve the interconnect. If the alignment accuracy is not good, you could have electrical deformation. I am going to move on to the conclusion of this presentation. Hybrid bonding has proven to be also used as a scaling method, which is employed to increase the package integration and also to improve the functionality of the component. So here we can see, we saw that we could actually have improved device properties like the efficiency, the reliability of the component, and the increased speed like high bandwidth for memories. Also, we cannot ignore the challenges that this type of technology has, like the alignment challenges and the surface defects that could actually reduce the yield. As hybrid bond pitches get smaller with all the components that they are making, surface defects and bond pad alignment challenges cannot be ignored at this moment. Hybrid bonding could actually become a high potential for different applications, as we saw recently YMTC adopting this type of technology for their memories, and it becomes it's going to be more and more adopted by different players to actually improve their components and devices.
Okay, now it's time to welcome our last speaker. So Max Min, please.
Okay, so thank you. So today, okay, thank you. So today, let me introduce the cube technology for heterogeneous integration. So first, so let me define the cube. So from our side, the cube is a passive and active interposer device connecting cubes, such as chips, chipnets, and components, and horizontally and vertically for heterogeneous integration for their mobile and 5G and wearable, HPC, and AI applications. At the center, you can see the cross-section of a conventional package with the cubes. Okay. In the conventional package, you see you have, I would say, logic die, and then memory die, and then the substrate. But right now over here, we are trying to develop the, I would say, X cube, I cube, R cube, and the E cube and H cube technology, helping to connect to the logic to logic, and the logic to interposer, and also the logic to HBM memory, and also we are trying to connect the substrate to the system board. So let me talk about those cube technology on the right side. So the first thing is the X cube. So X cube is based on the 3D logic TSV. Since this X cube can stack the logic die vertically, and because of that, we can enjoy very high integration capability, and also we can enjoy the small form factor. Okay, and then second group is showing the I cube, R cube, E cube. So I cube stands for a silicon interposer. So silicon interposer can have ultra fine pitch interconnect, and also silicon interposer can be 1x, 2x, 3x, and then now it's 4x electrical size of a silicon interposer. And then by having this, I would say 4x electrical interposer, then you can enjoy very large package. Okay, and you can accommodate more HBMs in the I cube. Okay, and then R cube is for based on the RDL interposer. So by nature, RDL actually is already thick enough, okay, which is a thick copper, which is around 3 micrometer or so. And also RDL interposer, there's no TSV, that's why the TSV list. So thanks to the low TSV, and then RDL interposer is cost effective. And the last one is the E cube. So E cube is this technology is based on the fan-out PLP technology. And then rather than have a SOC silicon in the fan-out PLP, we trying to embed a silicon bridge. Since we can have a silicon bridge in the panel, then you can have a very flexible, I would say, silicon bridge, which has a different number of layers and also different pitch, okay, for the connection between the logic and logic or logic to HBM. And this panel technology is the panel size, which means you can enjoy the very high volume production. So I'll talk about this I cube, R cube, and then to E cube later on. And the last one is H cube. So H cube is more likely for making the very, very large package, okay, large package size. And this H cube will provide a very good balanced power, performance, area, cost benefit. Okay. So now let's talk about X cube. So X cube stands for extended cube. From Samsung point of view, there's so many products we developed. So first one is, I would say, the Samsung Mobile Exynos SoC chip, okay, based on the TSV SiP. And then second one is a DDR memory with a 4-stack TSV, okay. And then third one is HBM2 and 2E. And then the fourth one is a CIS image sensor with a stack. And all this technology actually using the micro bumping technology, and then sooner or later we're going to enjoy the hybrid bumpless technology. So before we keep moving forward, Samsung Foundry also add one product series called X Cube. So X Cube also can enjoy the micro bump and then bumpless technology. So let me share where we are regarding the X Cube micro bump and then bumpless. So the micro bumping usually in general say the pitch is 40 or 25 micrometer. So 40 means it's more like a deck to phase bonding through TSV. That's why we're having a 40 micron pitch. And the phase to phase bonding case, there's no TSV for the logic to logic connection. That's why you can enjoy 25 micrometer pitch. So this 40 and the 25 micrometer pitch X cube is already mass production ready, and then already mature enough. And also we have a manufacturing infra, which means that we can develop the product. And then based on this mass production infra, that we already demonstrate the 3D SLM functionality based on the 7 and 5 nano silicon. Now let me talk about the bumpless technology, so hybrid bonding. So for this technology, we are under development along with the 2.5D and 3D. So what I mean by 2.5D is actually trying to stack the 3D logic X cube on top of a 2.5D interposer. And this X cube is more likely based on the face-to-face bonding. Okay, that's why we can enjoy the 10 micrometer or less bumpage. And then since this is hybrid bonding connections, then we can enjoy very high thermal performance. Now let's talk about 2.5D cubes. So I cube, R cube, E cube. So on the left, you can see the top view of a silicon interposer of I cube. And I already mentioned about the features of this silicon interposer, now R cube. And at the bottom, you can see the cross section of the E cube. So as you can see there, silicon bridge is embedded into the fan-out PLP. Okay. From Samsung point of view, we have two assembly process. I would say the COS and COW. So let me explain a little bit about this COS and COW. So COS is based on the interposer chip, okay? And basically we have a wafer and panel, and then we cut it as a chip. And then we directly mount this chip on top of a package substrate. That's what we call the COS, okay? And then we mount the logic and HBM, and then we can do the interim test in between. Okay, that is a COS. And the COW actually is based on the wafer or panel, okay, use it as a carrier, and then we attach logic and HBM on top. And then after molding it, then we do a sewing, and then we cut it, this one as a one piece, and then mount on the package substrate. So by using two assembly process, also several type of, I would say, interposer technologies, and plus a different number of HBM. So we already developed so many, I would say, test vehicles as well as a product. So on the right side, you can see the iCube2 and iCube4 and iCube8 type of a package. So all the way bottom, you can see the 85 millimeter package with a 4x, almost a 4x electrical with a 8 HBM2E, I would say, cubes. Okay. So this is a summary of our 2.5D interposer. And next one is H-cube. So H-cube, as I said, is a concept is simple. So we are trying to make large package. Okay, so in general, I would say, HDI substrate all the way bottom, actually this size is can go up to 200 millimeter package size. But we can accommodate many packages or components on top of it. So the concept over here is rather than have I would say large package substrate, we're trying to make it smaller. That's why we said a smaller substrate, and then we can enjoy this I would say smaller PGA pitch, and also you can embed the passive or active into the package substrate. And then over there, then we just mount the entire this package substrate stuff on top of HDI substrate, and then we can make it compatible with the motherboard system BGA pitch. And then within the on top of HDI, we can mount many packages or many components, and then we can enjoy the higher integration in a package. That's why we are trying to make it ultra high integration products. So this is my last presentation. So hopefully this presentation helps for you to understand what we are trying to do based on CUBE technologies.
Thank you very much, Max, for this very nice presentation. We received many questions that we are about to answer now. Let's start maybe with you, Favier. What is the impact on OSATs and substrate suppliers if big players like Samsung, TSMC, and Intel are eating the lunch of advanced packaging revenue?
Hello, Faisal. Thank you for the question. So yes, this is especially true mainly for the high-end application domain. Big players like Samsung, Intel, and TSMC have successfully tapped into advanced packaging market revenue growth, and they have achieved a faster time to market than OSATs. So you see, fabless is getting attracted by the prospect of cutting-edge turnkey services, meaning to say the latest silicon node manufacturing technology is combined with the elegant way of doing the packaging, right? This can help to scale Moore's law at package level. So if the bigger players can provide both the quality and cost benefits for the high-end application, then OSAT may have to stay on the defensive side of this business. So on the other hand, a possible path forward is probably for OSAT to continue to innovate significantly, critically, and secure the key IP for the next generation of the packaging technology. Having said that, it's really hard to have this combined development without the front-end dive. So for OSAT, big investment moved by big players may really prevent or even deter OSAT decision to invest in the same direction. So in general, we believe because of this impact, the OSAT may stay on the sideline for now for the leading edge packaging business, which involves front-end synergy. Then for the substrate supplier side, the situation perhaps has been reshaping on the boundaries for substrate suppliers, because if the industry moves entirely from substrate level based packaging to wafer level based packaging, the substrate business will be eaten up by wafer level packaging houses. Like for example, Intel has enabled EMIB, and with high-end substrate suppliers like Shinko, Ibiden, and Samsung, as mentioned by Max, they have the H-Cube, and we also know that there have been a lot of innovations in the substrate level, and has also taken panel level fan-out in-house. So, and of course, we know that TSMC has been working with Unimicron on the substrate level developments. However, and this is what we are seeing now, and this reshaping the boundaries. However, if the industry is pushing the substrate players to innovate by themselves, then there's a chance for them to actually get involved and capture the market share for high-end packaging. That's all.
Yeah, thank you. Very clear. Thank you very much, Favier. We have another question. We have another question maybe for you, Belinda. You talked about the pitch reduction. Could you please comment on the TSV high aspect ratio?
Okay, thank you for that question. Actually, let's look, we had two components that I showed in my presentation. We had the NVIDIA A100 and the Tesla V100. So when we looked at the DRAM TSV that we had, for the Empire A100, we had a length of almost 50 micrometers, and the thickness, or we can say the diameter, was around 4.7 micrometers. So this brought to almost a high aspect ratio of 1:11. So this actually was an increase compared to Tesla V100 that had a length of the TSV length was 58 micrometers. And also the thickness was quite bigger because this is the old generation. The TSV had a diameter or a thickness of around 5.8, and its aspect ratio was calculated to be almost estimated at 1:10. So we see a slight increase from one generation to the other, and we think this increase could actually go on with each generation. Thank you. I think that answers the question.
Yes, thank you very much, Belinda. Max, we have one question for you. In X-Cube, is there any plan to stack memory on logic?
All right. Okay. Thank you. Good question. So memory, I think SRAM memory, we already talked about it. So I think the memory means DRAM memory. Yes. So Samsung Foundry is ready to stack the DRAM memory on top of our logic. But what we need is a DRAM wafer with a TSV. So far, a lot of people have a technical challenges stack the DRAM memory on top of a logic, I would say, die, because of, I would say, from a thermal point of view, this is challenging to stack the DRAM die on top of a logic die. So I think we got to solve all these technical problem first, and then later on we can stack the really stack the DRAM memory on top of a logic.
Okay. Another question, why use hybrid bonding for 3D SoC? Javier, that will be for you.
Hello, Faisal. Thank you for the question. We know that for the typical 2.5D 3D stacking to be achieved, is usually attributed to the TSV technology. However, in most of the application, TSV are larger in size for the dense architecture and is limited by the overall size itself. So the metal filling of TSV can be quite complex, and for a lot of manufacturers, it requires a very strong technical know-how and front-end investment. So to overcome these limitations and heavy investments, industry players have started to look at other solutions. For example, one of the technology is Xperi's hybrid bonding technology, which entered the market in 2016 through the Sony's CMOS image sensor in Samsung Galaxy X7 mobile phone. So this capability to achieve interconnection with a pitch lesser than 2.5 micrometer has been the key factor and the driving motivation for the industry to look into this. So with this key milestone in mind, entering the CIS hybrid bonding, this technology has been really to be able to put together the small interconnection pitch and stack different memories or memory on logic with low thermal budget. And this can be very attractive for the technology as a path forward to achieve like multiple stacks of memories and processors. So, at system level, this 3D packaging has been really critical and be crucial. So for it to be like, to go to the next step where we have the partition, 3D SoC to be packaged, these dimensions of the interconnects is expected to move to 10 micrometer and below. So, with all this manufacturing limitation for solder bumps and with the reduction of bump pitch, bridging with the neighbor bumps and full intermetallic compound joints are all prone to like shorting or necking, especially once you're looking at below 10 micrometer pitch. So to one of the way really now to be able to connect them at such a lower pitch level is through hybrid bonding. And among these different packaging technologies, we know that hybrid bonding wafer to wafer has gaining a lot of interest, and not only is it because due to its high integration density capability, but it also offers the Z-axis direction integration, right? The top and bottom stacking. So it has a benefit in terms of XY footprint and also the Z direction. So this is one of the really key, very key reasons why hybrid bonding is emerging as a fine pitch interconnect solution for 3D SoC. So I hope my answers are clear. Thank you.
Yes, thank you. Thank you, Fabier. Another question for you, Max. Thank you, Fabier. Yes. Another question for you, Max. Which 2.5D cube will be good for HBM3 integration, die split, and SerDes chiplet?
Okay, that's a good question. So, okay, HBM3 integration. HBM3 is under development right now. Okay. Okay, and a lot of people talking about chiplet, or our SerDes chiplet with the die split. So based on our experience so far, we think iCube is the best fit for the HBM3 and the die split and the SerDes chiplet integration. Okay, that's how we think.
Okay. Maybe we have time for a last question, as we receive a lot of questions, but time is run over. For Belinda, that will be for you, I guess. For the HMTC 3D NAND, how many metal layers does the CMOS wafer and the NAND array wafer have?
Okay, here we're looking at the YMTC 3D NAND memory. So usually you have 5 metal layers for the different manufacturers that have been using the CMOS periphery and the NAND array on the same wafer. They had 5 metal layers, but here you have 2 different wafers. So the CMOS wafer had 4 metal layers, 1 tungsten, and 3 of them were in copper. And the NAND array wafer had 3 metal layers. So here we see that the CMOS wafer needs metal layers to actually connect with the different transistors, and hence afterwards make bond pairs with the NAND array wafer. So the NAND array wafer also needs its own metal layers that had 3. So in total, I can say this type of hybrid bonding device, it had 7 metal layers, where the 4th metal layer of the CMOS and the 3rd metal layer of the NAND array wafer were bonded together. That's where the hybrid bonding takes place, in the last metal layers of each wafer. I think that should answer the question.
Thank you, Belinda. Thank you very much. The webcast is now ending. Thank you to all our presenters. Thank you, Favier. Thank you, Belinda, and thank you, Max, for your time and analysis and also answer. We have a lot of questions, but we'll answer to the remaining one by email soon. To everyone, you will soon receive an email with the recorded session within 24 hours. But please note that the presentation is already available and can be downloaded from the resources section of the platform on the bottom of it. Feel free to share the presentation with colleagues or send them the link to access the replay. Finally, please let me remind you that you can find all our reports and monitors on our website, www.i-micronews.com. Do not hesitate to contact us if you have additional questions. You can find our contact details on the last slide of the presentation. Thank you all for joining us today. Have a good day and take care.